Sometimes, no matter how innocent-looking a statement is, it just feels downright impossible to prove it using any of the techniques that we have learned. If you ever find yourself in that kind of situation, then perhaps you want to consider the method of proof by contradiction. If we want to prove that P is true, then we first assume that P is false. Then, we try to make deductions to a point where we reach a contradiction. Since all the deductions are logically sound, it must be the case that our initial assumption that P is false must be wrong. In other words, P must be true, which is what we want to show. Suppose we want to prove the inequality square root of 5 plus square root of 3 is less than 4. What we shouldn't do is the following. Since square root of 5 plus square root of 3 is less than 4, we square both sides to get the square of square root of 5 plus square root of 3 is less than 4 squared, which means 5 plus 2 square root of 15 plus 3 is less than 16, or 2 square root of 15 is less than 8, so square root of 15 is less than 4. We square again to get the square of square root of 15 is less than 4 squared, or 15 is less than 16. This is true, so square root of 5 plus square root of 3 is less than 4. All of these are nonsense because the first line that we started with is the result that we are trying to prove, so we cannot assume it is true and work from there. In fact, a correct proof is to simply change all the signs to greater than or equal to. That is, we first assume that square root of 5 plus square root of 3 is greater than or equal to 4, which is the negation of the wanted result. Then, we proceed to do the things above. We get to 15 is greater than or equal to 16, which is, of course, a contradiction. Since all the steps starting from the second line are logically sound, it must be the case that the first line, that is, our initial assumption that square root of 5 plus square root of 3 is greater than or equal to 4, is wrong. So the opposite must be true. In other words, square root of 5 plus square root of 3 is less than 4, as required. Let's look at another example. We want to show that square root of 2 is irrational. Again, we assume that the opposite is true, that square root of 2 is rational, and then look for a contradiction. We can write square root of 2 as the fraction of two integers a and b, where b is non-zero. Here, for reasons that will be apparent later, we assert that a and b have no common factors other than 1. In other words, the fraction a over b is in its simplest form. We can do this without loss of generality, because we can always reduce a fraction to its simplest form by dividing its numerator and denominator by the highest common factor. Now, square both sides to get the square of square root of 2 equals the square of a over b. So 2 equals a squared over b squared, or 2b squared equals a squared. Let's label this equation as star. Since a squared is 2 times an integer, we know that a squared is even. In other words, a times a is even. Then a cannot be odd, since an odd number times an odd number is again odd. So a must be even. This means that we can write a as 2 times k for some integer k. We can substitute this expression into the equation star to get 2b squared equals the square of 2k, which equals 4k squared. So, dividing both sides by 2, we have b squared equals 2k squared. This means that b squared is even, and using the same argument as a squared, we know that b must be even. But now we have a is even and b is even, so a and b have a common factor of 2, which is a contradiction because we have assumed that a and b have no common factors other than 1. So, our initial assumption that square root of 2 is rational is false. In other words, square root of 2 is irrational. Now, consider the statement P implies Q. If we want to prove it by contradiction, we would have to assume that its negation is true. Recall that the negation of P arrow Q is equivalent to not P or Q, which is equivalent to P and not Q. So we assume that P is true and Q is false. If we can reach a contradiction, then we have proved P implies Q. An example of contradiction is we can show that P is false. In this case, we have shown that not Q implies not P, which is equivalent to P implies Q. Let's look at an example. Suppose we want to prove that if n squared is odd, then n is odd. To prove by contradiction, we assume that n squared is odd, and n is not odd. That means n is even. So we write n as 2 times k for some integer k. Then we can compute n squared, and if we can show that it is even, then we will have a contradiction. Now, n squared equals square of 2k, which equals 4k squared, or 2 times 2k squared. This is clearly even, so our proof is complete. Let's consider another example. We want to prove that if x is rational and y is irrational, then x plus y is irrational. So we assume that x is rational and y is irrational. Then x equals a over b for some integers a and b, where b is non-zero. Assume for a contradiction that x plus y is rational. Then we can write x plus y as m over n, where m and n are integers and n is non-zero. Now, we can write y as x plus y minus x, which equals m over n minus a over b, or bm minus an over bn. This is clearly rational, which is a contradiction since we have assumed that y is irrational. So we must have x plus y is irrational.